Welcome to tutorial 7, where we're going to talk about the ocean's role in the climate system. So one of the largest roles of the ocean in the climate system is contributing to meridional heat transport. So as we discussed in previous tutorials, because of Earth's tilt, the equator receives much more insolation than the poles. The plot on the left is a plot that you've already seen before. We see the incoming and the outgoing radiation. And this kind of implies that there's a heat transport by the climate system. So for example, at the poles, the incoming radiation is much less than the outgoing radiation, and this is because there's transport from the equator to the poles by both the ocean and the atmosphere. On the right plot, we're looking at the annual mean northward energy transport. The black is total, and then the red is atmosphere, and the blue is ocean. And so let's first look at the total line. We can see that in the northern hemisphere, we're transporting energy northward, and in the southern hemisphere, we're transporting energy southward. So this is what we were talking about equator to pole heat transport. And then near the equator, we see that the ocean transport is quite dominant. So this is blue. And then as we get further away from the equator, we see that most of the heat transport is done by the atmosphere, which is the color there in red. And just to note about what this ocean transport is, this is kind of achieved by all of those circulations that we talked about in previous tutorials. So we get that northward heat transport because of the circulation, including the thermohaline circulation and the wind-driven circulation. Okay, so the ocean doesn't only contribute to this through its own circulation and its own transport. As we'll talk about on the next slide, the ocean contains much more heat than the atmosphere. And so in addition to doing some of this heat transport on its own, the ocean also transfers heat to the atmosphere, particularly in the mid-latitudes, for example. So the plot on the left is showing the net heat flux in or out of the ocean. Here, blue colors means a transfer from the ocean to the atmosphere. So we can see that away from the equator, say if we were to focus on like 45 degrees north, the ocean is transferring heat to the atmosphere. And even though the atmosphere is carrying that heat northward, some of the heat is coming from the ocean. And so this combined ocean-atmosphere system is really what sets a lot of the current climate, where we have this distribution of temperature across the globe. So let's talk more about what we mean when we say that the ocean can hold more heat than the atmosphere. We can define this quantity called the heat capacity, which is basically the amount of heat in joules that's necessary to raise the temperature of an object by 1 degree Kelvin. And we can talk about the specific heat capacity, which is the heat capacity per unit mass. In the table on the right, we see that we've listed specific heat capacities for the atmosphere and the ocean. And we can see that the ocean has a specific heat capacity that's about 4 times that of the atmosphere. So what that means is it takes about 4 times more heat to raise a kilogram of ocean water 1 degree Kelvin than it would to raise a kilogram of atmospheric mass by 1 degree Kelvin. And these can combine into the total heat capacity of the system basically by multiplying by the mass. So in the middle column, we've listed the mass of the atmosphere versus the ocean. We see that the ocean is much more massive than the atmosphere is. And this results in total heat capacities that's shown in the right column there, where we see that the ocean has a heat capacity that's about 1,000 times that of the atmosphere. And so this means that the ocean is really a dominant force in the climate system in terms of absorbing energy. And we'll talk about this in terms of anthropogenic climate change. So since pre-industrial times, ocean heat uptake has modulated changes in surface air temperature because of anthropogenic climate change. It's absorbed about 90% of excess heat. And this plot on the right is showing this idea. So the x-axis is time in years, and the y-axis is energy change in zetajoules. So here zetajoules is 10 to the 21 joules. The blue colors are showing the energy change of the ocean, and then we can see other aspects of the climate system. Also, we can see land in brown, ice in gray, the atmosphere is shown in purple. But this is really demonstrating what we were talking about, that there's 90% of the excess heat has gone into the ocean, and that can be seen from the plot on the right. Something else we haven't talked about much is that the ocean also takes up carbon dioxide. So it's taken up about 25% of human emissions. And these two things these two things combined, that the ocean is taking up both heat and carbon dioxide, modulates the amount of surface air temperature change that happens because of CO2 emissions. The other thing I want to talk about here, and can be visible in the plot on the right, is that the heat change in the ocean is largely happening in the upper ocean. This is something that you'll explore more in the tutorials as you look at ocean heat content over time yourself. But basically the idea behind why this is happening is just because this is the part of the ocean that's in contact with the atmosphere. So the ocean in general is a much slower system in comparison to the atmosphere. And this can be seen from the plot on the right, which is looking at mean age of water masses at 1,000 meters depth. And by mean age, what we mean is how long it's been since that water was last in contact with the atmosphere. So we see in some regions the water is younger at 1,000 meters. So for example, in the North Atlantic, where we've talked about previously, this is where the overturning and the thermohaline circulation happens. We see that the water was last in contact with the atmosphere much more recently. If we look at the yellow areas, which is areas of a lot of the Pacific, the water at 1,000 meters depth hasn't contacted the atmosphere in 500 years. And so this kind of explains why much of this heat increase is happening in the upper ocean, because the waters below that basically just haven't contacted the atmosphere since that increase in heat in the atmosphere. So these are all kind of ideas that you'll explore more as you look at heat content in the tutorial that follows this. Good luck.